In the last session, we looked at the sorting problem. So, given a sequence of numbers, the sorting problem has to rearrange the sequence so that the sequence is in increasing order. We sought two algorithms to do that, an insertion sort algorithm and a merge sort algorithm, saw the analysis of them, the worst case, the best case and the average case. In this session, we will look at tree data structure and see how that can be used in solving this particular problem. So, a tree data structure is something that we have already looked at. We have also looked at special type of trees which were a proper binary tree and a complete binary tree. So, I will just recollect, we have already seen these definitions. So, you have proper binary tree and then we had looked at complete binary tree. In a proper binary tree, all the levels are always completely filled, in the sense every internal node will have precisely 2 children, whereas in a complete binary tree, except for the last level, all other levels are completely filled and the last level is filled from left to right. We also saw some properties of a proper binary tree. There is another property which is going to be useful, which I am going to state now, and we are going to use tree for sorting procedure. The property is if I look at a number of external nodes in a proper binary tree, it is always one more than the number of internal nodes. So, number of external nodes is actually equal to number of internal nodes plus 1. So, this is a crucial property that I am going to use today in using tree for sorting process. We also had seen how to use array to represent complete binary tree. If you recollect, if you have a complete binary tree or a proper binary tree, one can use array to represent it. And so, if you have an array or if you have a complete binary tree, say for example, I have a complete binary tree and so I have a complete binary tree which saves. So, at each node you have the data that it is going to store. So, at this node you have 4, 6, 8, 2, 1 and 5. We had seen that array that it will represent this is right. So, the root will be the first element, right, and if you have I, its left child, right. So, its left child is going to be at the 2ith location and its right child is going to be at 2i plus 1th location. So, this will be, so you will have 4, 6, 8, then the left child of 6 is 2. So, that will be here followed by 1 followed by 5. This is again just a repeat of the last. I am going to use this idea again. So, it was just to recollect. So, given a complete binary tree, we can write down the array representation. Given the array representation, one can construct back the complete binary tree that it is going to represent. So, these are few of the ideas that we are going to use to try to use trees for sorting a sequence of numbers. So, the algorithm that we are going to look at is called a heap sort algorithm. So, we are going to use something called a heap data structure. So, heap is a complete binary tree. So, it is a complete binary tree with an additional property called the heap property. Right. So, this is called a heap property, which says that if I look at the ith node, so if you look at the key stored at the parent node is always bigger than or equal to key stored at the child node. At child. That is the heap property. That means the keys that are stored at parent nodes are always bigger than or equal to keys stored at the child node. This also is called a max heap. So, similarly, we can have a min heap where the heap property is reversed, that is key stored at parent is less than or equal to key stored at the child node. Such heaps are called min heaps. What we are going to deal is with max heaps. So, I am not going to drop the word max, we will just stick to the name heap. For us, heap is always going to be the max heap. It is easy to observe. Right. So, let us try to illustrate. I am going to try to illustrate a heap and try to see what are the things that we can deduce directly from the definition of a heap. So, heap has to be a complete binary tree to begin with. So, let us try to put a complete binary tree. I am going to draw a little more complex figure. Okay. So, it is a complete binary tree. If you can observe, up to second last level all the levels are filled, only at the last level your nodes are filled from left to up to a certain point. Now, let us try to introduce the keys with the heap property. It is easy to observe that the root, which is the parent or the ancestor of all the other nodes, is going to have the largest key. So, let me put 16 here. This can be 10, 7, 3. This can be 12, 9, say 6, 5, say 2 and 4. Now, you can see that this is a complete binary tree and it satisfies the heap property, that is the key stored at the parent is always bigger than or equal to key stored at the child node. If I am simply going to replace say this 6 by 8, then it is easy to see that this is not a heap, because at this particular position your heap property is not satisfied. That is, you have a key stored at a child bigger than the key stored at its parent. So, such an example is an example of a complete binary tree which is not a heap, that is, it violates the heap property. So, one key important observation is that the root, right. So, this is an important observation, that the maximum key is stored at the root. So, if you have a heap, the root will always store the max key. So, what we are going to do is look at the heap, define 3 procedures on them. So, the ones that we are going to define are, we are going to look at what are called a procedure called an heapify. That means, if you have a complete binary tree in which a heap property is not satisfied, how to mend it and how to make it into a heap. That is going to be a procedure which we are going to call as heapify. We are going to do another procedure which is called a build heap. A build heap procedure is going to be a call of heapify, so that given a sequence of numbers, we will see how to construct a heap which is going to represent that sequence. And the third procedure that we are going to do is combine heapify, build heap and write down precisely what is called a heap sort algorithm. So, we are going to try to look at these three procedures: heapify, build heap and heap sort. So, as I said, the first step is, if the heap property is not satisfied, how do you make sure that that it becomes a heap? So, let me try to work out with an example. So, let us see, try to modify this example. Let me see if I can have, I will change this particular point and try to introduce something that is going to violate the heap property. So, let me put here a number 3. Now, what we see is, if I start looking for the complete binary tree from the leaves, what we know is one node trees are always heaps, right. So, just a small observation that we are going to use is one node trees are always heaps, are always a heap. So, if I start from the leaves 5, 4, 2, 3, 7, these are always going to be leaves. Now, let us try to look at here. So, at this particular stage, this also is a, if I look at 6, it at this particular point the heap property is not violated. If I go here 9, at this point also the heap property is not violated. Similarly 10, now as I reach here, say I am going to call this as I, the heap property is violated, that is, you have the key at the parent less than the left and the right. So, at this particular point we are going to try to modify so that the heap property is satisfied in the modified tree. So, I am going to look at the procedure which is called heapify, to which we are going to pass two arguments, an array A and an index in it, right. So, at heapify we are passing two arguments A and I, such that at I the heap property is violated, and important, we are going to assume that precisely at I, if I look at the left subtree and I look at the right subtree, both are heaps, right. So, if I look at I, at which the heap property is violated, you look at the left subtree and right subtree, both are heaps, correct. So, the important assumption to call the heapify procedure is, we are going to assume that at I, correct. So, at node I, your left subtree as well as the right subtree both are heaps, these both are going to be heaps. So, this is an important assumption in the heapify procedure. So, what we are going to try to do is try to restructure our heap so that the heap property is satisfied. So, let me just redraw the figure from here. So, 1. Okay. So, this is at this particular point your heap property is not satisfied. Now, what the heapify process does is it allows the node I at which heap property is violated to float down inside the tree. So, the process that we are going to do is sort of at the point where your heap property is violated, we are going to allow that to float down into the tree. Right. So, what is going to happen is the following. So, we are going to restructure our tree as follows. So, we will look at 3. At this particular point, we know the heap property is violated. So, I am going to put this as it is. This tree is not going to change. So, I am not worried about it. So, I am going to copy this as it is as the right subtree there. At 3, we allow this to float down inside the into the tree. So, you 3 you float it down. So, both 9 and 6 are bigger. So, I will choose the bigger one and swap it with 3, correct. So, what we are going to do is the following. So, both the left as well as right are bigger. I will choose the one which is largest and swap it with 3. So, I will put 9 here. So, this does not change. So, I will have 6 and 1. Now, as 3 comes here, correct. So, if I have 3 here instead of 9 now, correct. So, if I have 3 here, say 4 and 8. So, now if I look at this particular node, again the heap property is violated there, because 3 is less than both 4 and 8. So, we still again let 3 float down into the tree. So, the next step is going to be, so in the same tree now we are going to again modify in following manner, correct. So, the next step will be you are going to have, so as your 3 goes there, I am going to bring 8 here, 4 and 3. Now, we see that this precisely is a tree. Now, I can, this anyway is not touched. So, we can draw it as it is. Now, if you look at this particular tree, this happens to be a heap. So, this procedure is called a heapify procedure. So, given, so the two parameters are going to be A, the array, and the node I at which the heap property is violated. The heapify procedure allows the node at which the property is violated to float down into the tree, so that the modified tree will have the heap property. So, that is the first procedure that we are going to look at, which is called a heapify procedure. The second procedure will use heapify procedure to construct a heap out of a given array. Right. So, given a sequence of numbers which is represented using an array, calling the heapify procedure, we are going to construct a heap which later would be used for sorting purpose. Right. So, let us try to start with the array, an arbitrary array of say whatever size 10. So, this is 1, 2, 3, 4, 5, 6, 7. I need 3 more elements. And see 1. Okay, I am starting with a 10 element array. Using this 10 element array, we are going to see how heapify will be used to make a heap representing this array. The first step, so the first step is, given this, try to make a complete binary tree which is going to represent this, and that we know, correct. So, the first element is going to be the root, then we know for ith index, the 2ith index is going to be the left child and 2i plus 1th index is going to be the right child. So, let us try to do this. So, I am drawing a complete binary tree which is going to represent this number. So, this 10, it is 9, 6, children of 9 are going to be 3 and 11, right. So this is say 1, 2, 3, 4. So if I look at 9, its left child is at index 4, which is 3, and its right child is going to be the key which is stored at index 5, which is 11, and I can just continue this. Now for 6 it will be 15, then 4, this is going to be 16, 8 and 1. So what we have is, first step is given an array. So my first step is construct complete binary tree, which may or may not be a heap. So the first step of your algorithm of make heap is to, given an array, construct a complete binary tree representing that array. Now what do I know is the following. I am going to use two things that we have already stated earlier. We are going to try to make this into a heap, and it is going to be a bottom up approach, correct. So what we are going to do is, we are going to do a bottom up approach, that is, we will start from the leaves, try to check where the heap property is violated, rectify it there and move ahead. What we know is the following, that all these particular nodes which are leaves, which is 1, so all the leaf nodes which are here or external nodes, they are all already heap. So we do not have to check heap structure up to here. Now I know number of leaves is precisely going to be, correct, we had seen number of external nodes is number of internal node plus 1, correct. So what do I know is, from this array all the elements from this particular point n by 2 plus 1 to a n. Let me assume n is even. If n is not even, one can replace this by the floor of n by 2, right. So not much changes. If n is odd, I have to simply replace n by 2 by ceiling floor of n by 2. To make things simple, let me assume n is even, right. So n by 2 is an integer. So what do I know is, in a, if I have this array, from a n by 2 plus a n are going to be leaves of the tree. So all these elements are going to be leaves. So you do not have to check the heap property at these points. So the heap property will be checked only from a n by 2 so the heap property will be checked only from a n by 2 until a 1, correct. So we are going to check, so we are going to check heap property only from a n by 2 to a 1, right. So that is going to be here. So I am going to start so from here, this is the first node that we are going to check for the property heap. Now if I look at this, this already is a heap, correct. So this is also already bigger than its parent from the key at its child. So this is already a heap. So you do not have to modify the structure here. At this particular thing, your heap property is already satisfied. So we move to, so we move I here. Now at this particular point, we see that the heap property is violated. 3 is less than both 16 and 18. So the key at the parent node is less than key at the child nodes. So we will rectify this heap property here, right. So let me rub this now. I will try to draw the corresponding tree So, at this particular point your heap property is, so you will call heapify here, correct. So, and rectify the property here, and it is here you will let it float down. So, I will have 10, let me put this. So, instead of 3 I will get 16 here, and you will get 3 and 8, this is going to be 11, 1, whatever, 9, 6, okay, 15 and 4. So, we see that now you have the heap property satisfied here. Next you change your I here, correct. I is decrementing from n by 2 to 1. Right. So, here I initially was 5, then it is 4, now I becomes 3. Again we see that the heap property is violated here. Right. So, I am going to rectify the tree there itself. So, again we are going to call heapify procedure. After heapifying procedure, this tree at this part is going to be modified. Right. So, let me do that. So, the keys here we know already. So, we will have 15 here, 6 and 4, and I moves here. Right. So, we are checking. Now, again we see that the heap property is violated there. Right. So, in this particular case what will happen is we will allow 9 to float down. So, it will it is less than both 16 and 11. So, we will swap it with 16. So, 16 will go here, 9 will come here, and at this particular stage the heap property will be satisfied. So, I can just replace this now. So, this is going to be 16 and this is going to be 9. Right. So, let us try to just change this particular things. So, this is 16 and this is 9. And I goes here, correct. So, now again there is a heap property violated at the root, you again heapify, correct. So, and finally you will get heap, correct. So, what you can do is now you can simply complete the final tree. Let me put this here. So, the final heap that we are going to get is going to be as follows. So, this 10 is going to be replaced by 16, you will get 10 here, and if 10 is here it is still less than 11. So, you still have the heap property not satisfied there. So, your 11 will move up and 10 will go here, and then you have 1 here, and now you see that the heap property is satisfied. This is 9, 3, 8, 15, 6 and 4. This precisely now is the heap which is going to be the representation of this particular array, correct. So, what build heap procedure does is it keeps on calling heapify n by 2 times, correct. It is decrement from a n by 2 to 1. At each stage it checks whether at that particular node heap property is violated or not. If yes, rectifies and decrements the counter. Keep on doing this n by 2 times. What you get at the end is a heap structure. Now, let us try to see what is the time required in these procedures, correct. So, we have done heapify procedure and we have also done max heap procedure. What we know is in max heap procedure we are going to use heapify n by 2 times, right. So, once we know the time required to do the hippify operation, simply multiplying it by n will give us the time required to do the build heap operation. So, I am going to keep this, I am going to work with this example. On the right hand side, I will just try to do the analysis of hippify and a max heap procedure. So, this particular example I am going to work with. So, I am keeping it on the board. What I am going to try to do is the analysis. So, as we see in the hippify procedure, a particular node, if my hippify procedure or in my heap property is violated at the root, the worst case is going to be the root is the least element and it has to float all the way down to the leaf of a tree. So, the worst case of hippify algorithm is going to be heap property being violated at the root and it happens to be the least key in that structure. So, it has to float down all the way to a leaf of a leaf node of the tree. So, the maximum number of times it has to float down will be equal to height of the tree. So, hippify procedure will precisely in the worst case take time which is of order of the height of a tree. So, what we are going to do is try to look at height of a complete binary tree. Of complete binary tree. What we are going to do is, if my complete binary tree, so we assume that it is going to store n nodes and h is height. So, we will have a relationship between n and h. So, if you have a complete binary tree with n nodes, we are going to have a relationship between height and the number of nodes. Now, what do I know is the following. If I look at this particular thing which is already a complete binary tree which has n nodes and height is h. From the definition of complete binary tree, we know that the number of nodes n. So, if the height is going to be h, then up to the second last level which is here, the tree is going to be full, and since the height is h, there is going to be at least one node which is going to be at the level h. That would give me the following. The number of nodes is going to be now 1 which is at level 0, 2 which is at level 1, so on until height h minus 1 is full. So, we will get 2 power h minus 1 this is up to the second last level which is completely filled. Now, since the height is h, that means there is at least one node at level h, and this happens to be less than equal to n. Right. So, this is a property that we get between h and n. Similarly, we can get a property, this is n is bigger than or equal to, or number of nodes is less than or equal to this. This is, that is, number of nodes can be n is going to be bigger than or equal to this. Similarly, you can get the other inequality, that is, what is going to be the maximum number of nodes possible in a complete binary tree. That means all the levels are full, correct. If all the levels are full, so we will get n less than or equal to 1 plus 2 plus 2 power h minus 1. That means up to last level it is full, second last, and also the last level is full. So, I get this is less than or equal to n and n is less than or equal to this. Using these two equalities, one can prove that correct. So, both together are going to imply, so that will require some school algebra, that H is actually of order log n. So, this is a crucial theorem or result that we are going to do. A complete binary tree which is going to store n nodes, its height is going to be of order log n. Right? That means, if you want to now write down find the running time of Hippie-Phi procedure, it is going to be order log n time, which is height of a tree. So, your Hippie-Phi procedure we know is going to be of order log n. Now, if I look at the build-heap procedure, then we are going to call Hippie-Phi procedure n by 2 times. So, this will be of order n log n. So, that precisely is the worst case analysis for Hippie-Phi as well as build-heap. Now, let us write down the final procedure, which is going to be using both Hippie-Phi, build-heap, and given a sequence of numbers, we will sort them in a increasing order. So, step 1 is going to be this. Right? So, now let us do the heap sort algorithm. So, look at the last procedure, which is called a heap sort algorithm. So, your first step is given sequence, right. So, given sequence, construct heap using building operation, using build heap. So, that is what we have seen already here, right. So, if I am given this sequence, by calling build heap operation, we can construct the heap. Right. So, step 1 is illustrated here. This is my sequence, which is an arbitrary sequence, and using build heap operation, we have constructed the corresponding heap. So, the heap sort algorithm, the first step is precisely this. Now, what we know is the following, is that the maximum key is stored at the root. So, I can, once we have this, we can also write down precisely the array which this heap is going to represent. Right. So, let us try to do that. I am going to try to write down an array. Now, we started with an arbitrary array, build a heap using build heap operation. For this build a heap, now I am going to write down the corresponding array that it is representing. So, I will have 16, its child are 11 and 15, correct. 11 left child is 9, right child is 10. So, at 11 you have 9 and 10, 15 the left child is 6 and 4. So, I will get 6 and 4. Now, you have 9, the childs are 3 and 8, 3 and 8, and finally 10 has left child 1. So, we started with an arbitrary array, build a heap. This is a array which corresponds to this complete binary tree or this particular heap. Now, what do I know is the following, that at A1 now in this particular new array, I am going to call this as A. In this, the maximum element is at the root. So, we simply swap these two elements. So, what we are going to do is, I am going to simply do a swap operation and put it at the end of the list. So, what we are going to do is the following. So, if I call this as array A, right, so if this is my array A, then I am going to simply swap, correct. In so So, swap A1 and AN. N is the number of elements that you want to sort. So, what we are going to do is simply swap A1 and AN. So, let me do that here. So, this okay. So, this will be 16 and this will be 1. So, this is my modified array. So, after swapping A1 and AN, your array is going to be this. What you know now is that A1 is maximum. So, from here we know now that AN is in correct place. This is because AN happens to be the A1 happened to be the largest element, right. This is because A1 was largest. Right. So, what has happened now is we have modified A such that this element at the end of the array is in its correct position. Now, we simply look at once we do this, I am going to simply look at now once you do this, you look at array now A from A1 to AN minus 1. So, you consider A1 to AN minus 1. We know that except for A1, now rest of the elements are part of a heap, correct. Now, what we know is this is easy to observe that the left subtree, the left and right subtrees of the root are heaps. So, only can happen heap property is going to be violated at root. Correct. So, let me illustrate this point. So, what we are saying is left, once we do this sorting, correct. So, I have 1 which is being now the AN was swapped with A1. So, this 1 has gone here now, right. So, let me illustrate this point, that I am going to try to illustrate this note, that left and right subtrees of the root are heaps. The only place where now heap property is violated is going to be at the root of the tree. Let me illustrate this point. So, after doing the swap, right, after doing the swap, your 1 will go here, right, and 16 is going to be not considered now, and we will have the rest of the tree is going to be the same. This is going to be 11, 15, whatever, 9, 10, 1, 3, 8, 6 and 4. I am going to drop 16 from my consideration. We are looking from only A1 to AN minus 1. So, only place where heap property is violated is at the root level. Below that, the heap property is satisfied. So, we simply heapify at that particular point, right. So, we simply heapify at the root location. So, sorry, this is not yeah. So, this precisely is there once you drop. So, this is not in consideration now. We are looking at only a1 to a n minus 1. Now, this can be made into a heap by doing the heapify procedure. So, if I look at 1 which is less than both 11 and 15. So, the max I will send it here, the 1 will go here, and again it is not satisfied. So, 6 will go here, right. So, let us, so this will be 15, this will be 6, and this will be 1. This will be 6, this will be 1. So, this precisely again now is a heap. Now, again you keep on doing this. Now, what do I know? So, this is now, if I look at this man, the new array is going to be, so I will maintain this. So, our 16 is out of consideration, which is in right position. Now, look at this tree. So, this will be 15 and followed by 11, 6, 9, 10, correct. Then 6 is 1 and 4, 1, 4, 3 and 8. Now, I am again simply going to, we know that 15 is the max element. So, we will simply swap now at this particular stage, we will simply swap a 1 with a n minus 2, correct. So, I am going to swap a 1 with a n minus 2. So, your new array will have 8 here and 15 here, and now you keep on repeating this procedure. What you do is you keep on at the ith stage, you will swap a 1 with a I. So, as you do this procedure n minus 1 times, you will get this sorted sequence. What do I know? In the first step, 16 was maximum. So, we swapped a 1 with a n. In the second step, we know 15 is the maximum. So, we swapped this with a 1 with a n minus 1, right. So, you will have 8 here, right. So, 8 will come here and 15 will go there. So, what will happen is following, correct. So, once I do this swap, correct. So, once I do this swap, I will get 15, let me, okay. So, 8 will go here, this is going to be my 3 and this is going to be 15. So, what do I know is these two are in correct position. So, 15 and 16 are in their correct position. Now, the same argument is going to be repeated for a 1 to, this is n minus 2. Again, the heap property might be, is going to be violated only at the root, heapify, extract the maximum and keep on doing this. So, this procedure will continue precisely for n iterations. We know each iteration requires heapifying at a root position, that is going to take you a log n time in the worst case. So, the heap sort procedure in all or in total is going to be requiring n log n time. Right. So, let us try to write down the analysis now. So, you have the procedure heap sort. So, the first part of this is build heap. Right. We saw this takes us order n log n time. After this, once you do build heap, we are going to extract maximum, max, and heapify the new array I A at index 1. This again we know heapify procedure takes time, and this you are going to do n times. We know heapify procedure is going to take you log n time. So, and doing this n times is going to give you order n log n. Therefore, total time in the worst case is going to be order n log n. That precisely is the heap sort algorithm. Right? The algorithm is simple to remember. Given a sequence or given a input, convert first into a heap by doing heapify and build heap. Once you have a heap, we know root is maximum, the key at the root is maximum, simply extract it, heapify again, extract the root, heapify, do this n times, and what you get is a sorted sequence. So, this is heap sort algorithm, which basically uses the tree data structure to sort a given sequence. Another popular sorting procedure that is used is again like merge sort, depends upon what is called a divide and conquer strategy. We are just going to try to give a so quick sort algorithm like merge sort uses or is based on divide and conquer strategy. Divide and conquer strategy, if you recollect, starts by dividing your problem into sub problems, solving the sub problems recursively, finally combining the solutions of the sub problems to achieve a solution of the original problem. So, what quick sort algorithm does is the following: starts with so the first step is the divide step. If you recollect divide and conquer step algorithms, the first step is the divide. So, in this divide step, your array is partitioned in two parts using a pivot element. So, what happens is, given a array, say for example here, you are going to try to make it into two parts using a pivot. the two parts are going to be as follows. Okay, so let me say part L1 is part 1 is all elements less than equal to x, where pivot is say x, and L2 are all elements which are bigger than x. Usually the pivot is chosen as the last element. Usually it is chosen as last element of array. It could be the last element of array or the first element of array, depending upon whatever is the choice. Can be proved that the analysis is independent of really which element you choose as a pivot. It can be even a random element. So, whether you choose the first or the last or the middle or any random element of the sequence, can be shown that final analysis they really do not matter. So, one has to decide what choice we are going to do. We are going to choose always the last element of array as a pivot. So, we are dividing L1 or array into parts L1 and L2. Okay, so, this is say L1, these are all elements bigger than equal to x, less than equal to x. This is L2, which is elements bigger than x. So, what we have done is given an array and a pivot element, partitioned the array into two parts. One is all elements less than equal to x, followed by all the elements bigger than x. Now, your recursive state, we are going to do this recursively. Now, we have two parts L1 and L2. To both the parts, we are going to apply the same quicksort algorithm. That is, now we will look at this array, partition it into two parts, one with all elements less than equal to pivot of L1 and all elements bigger than pivot in L1, and similarly for L2. Now, recursive stage is quicksort L1 and L2 recursively. Correct. So, that just means given L, now you simply are going to, so instead of now if I look at say L1, now you will choose a pivot in L1 and partition L1 into two parts, could be anything like this. So, say these are all elements less than equal to x1, which is x1 is a pivot in L1, and these are all elements bigger than x1. So, what we have done is L1 is partitioned into two parts. Similarly, I can partition L2 into two parts, and we keep on doing this recursively. We know this will keep on doing until your part has only one element in it. Correct. So, the base case is going to be that you have only one element in your partition or in a part, and that is going to be the base case for this. So, we are going to quicksort L1 and L2 recursively. In the combine step or the conquer step, since you are doing all your computations within the array itself, once you finish the recursive stage, you already are going to have a sorted array. Right? Since you are doing all these computations within array itself, so at the end of the recursive step, there is no combining step that is required. The sequence that you are going to get after this step, after the recursive step of divide and conquer, is going to be in a sorted manner. So, there is no combined step required in quicksort, whereas a combined step was required in merge sort. Let us try to see what is going to be the complexity of this algorithm. and try to compare it with the other algorithms that we have seen up till now. Remember, this is a divide and conquer algorithm. So, its analysis will be via using a recurrence relation. So, what we will do is try to write down the recurrence relation, which will be modeling the running time or the complexity of this particular algorithm. Now, if Tn represents the time required to sort n elements, then this is going to be equal to time is going to be equal to the number of parts that you have, that is 2, the sizes of them, plus time required to get the size plus time required to combine the solutions. In this case, there is no time required to combine the solutions. If you recollect, all your divide and conquer algorithm we said is going to be of this type. We want to find how many sub problems we have. Here we will have 2 sub problems. In this particular case, all your sub problems had the same size. That may not be true here. It can happen that your sub problems have different sizes, plus time required to divide into sub problems, plus time required to merge or time required to combine back the solutions from the sub problems. We had seen in this particular quicksort algorithm, there is no time required for combining. After you return back from recur step, your sequence is already in sorted fashion. So, let us try to now look at the best case and the worst case. So, let us try to look at first the best case. In the best case algorithm, your partition is going to be in exactly 2 halves, right. In the best cases, you will get 2 T n by 2. This would mean that your pivot at every stage of your algorithm happens to be the median of the sequence, right. So, I will get exactly 2 halves only if the pivot happens to be the median. Right. So, that is your L1 and L2. Right. So, you get exactly 2 halves. Similarly, L1 will be exactly 2 halves and L2 also will be exactly 2 halves. So, the best case is going to be every time pivot happens to be the median, correct. So, I will have 2 sub problems each of size n by 2 plus time required to partition. Now, if I look at time required to partition, it is easy to see that every element you have to compare at least once with the pivot, correct. So, this will be at least n, correct. So, this is partitioning time. Not precisely looking at the partitioning procedure, not difficult, but easy to see that the partitioning procedure will do n computations, because every element will have to be checked with the pivot and then try to put it in the right position. So, the best case is going to be precisely like your nearly like your merge sort algorithm. So, we know the solution of this recurrence relation is of order log n. We had seen this while doing merge sort algorithm. So, the best case is every time you get exactly 2 halves, and in that case it behaves like merge sort algorithm, that means complexity of order log n. Now, let us try to look at the worst case. The worst case algorithm is going to happen whenever your partition is skewed, that means you get a partition in which one part has n minus 1 elements and the other part has only one element. That will happen if your sequence is already increasing or decreasing, right. If your sequence is say an increasing sequence, then your L1 is going to be all of this and L2 will be only one element, right, because all the elements are, if it is increasing sequence, all the elements are less than the maximum element which is at the end. So, in this case you get a complete skewed partition, and this will happen if my sequence is already in increasing or decreasing order. This will happen at all the intermediate steps. So, finally, if you look at your procedure, this would mean this will be T n minus 1 plus n. Right. So, the complete, this is going to be T n minus 1 plus n. This because in the worst case you get a very skewed partition, that means one part has only one element and the other part has all the other n minus 1 elements, and this keeps on happening at all intermediate steps. This will happen, such a scenario will happen in increasing sequence. In decreasing sequence you will have L1 which will have only one element, L2 will have all the other elements, and so forth. It can be shown that in this recurrence relation this is order n squared. So, what we observe is in merge sort, in quick sort algorithm, the best case is n log n and the worst case is n squared.